Hello, it's ready for Math 210 Brief Calculus. We're going to get started with our first section, 10.1, talking about limits. And we'll look at them numerically and graphically. So first of all, the basic idea is something that's easy, but getting to the technicalities, getting them right is not. That's from the textbook, not for me. But I would agree with it. It is. There's some challenges here. So we're going to look at how to evaluate limits numerically, how to evaluate them at infinity, and graphically. The important part to remember is with functions, there's two parts. There's the input. The input is also the x value, the first part of the coordinate. Right, an ordered pair is a function x, f of x. So the first one is our input or the domain values. The second one is the output, the y value, and also called the range, the value of the range. So we can think of a point as x comma y. When we use function notation, we change y into f of x or g of x or some sort of thing. But remembering we're dealing with two coordinates that make up a single point, an input and an output. So with that in mind, let's take a look what happens. So what really is a limit? So when we're talking about limits, what we're doing is we're getting the input value, which is the x, we're getting it as close as we want, as close as you want to a particular value. So we're letting, you'll see this in the limit notation, we're letting x go to some number or infinity or something. We'll just say a, because you'll see this a lot. So a is some number. We're letting x get close to it. It gets close to a from both the left side and the right side. And what the limit is, it's what the output value is. So as we get close to here, what we're doing is, say this is on a graph, this is an x value, this a is an x value. What we're looking at is as we get close from the left and the right, the limit will be what y value we're getting close to. Okay, so what particular y value we arrive at. That's what the limit is. So we're going to look at functions where the limit and the function value is the same, and then we extrapolate onto what happens when something else happens, where the limit and the function value itself are different. It could be possible that a limit does not exist, and so we'll look at those cases. So first of all, in this case, we're going to take a look at a linear function, 2 plus 1x. Remember, the slope is 1, the y-intercept would be 2. We want to know what happens as x gets close to 3. Now, as we think of this, we're not really thinking of what happens when x is 3. The limit is what happens as x gets close to 3. So this is a concept. Now we do know that when x is equal to 3, okay, you plug in 2 plus 3, we get 5. It should be 5. That's the value. That's the function value at 3. Okay, but what we want to explore is what's happening as we get close. So how we explore, and again, the reason we do this is because we're going to look at functions where x would not exist potentially at 3. Okay, so we have our graphing calculator. Turn that on. We're going to put in the function 2 plus x. And what we're going to do is we're going to evaluate this numerically. So what I'm going to use is I'm going to use my table, which is in blue. But before I go to the table, I'm going to go to table set. And this is if you're using a TI 83 or 84. What I want to do is, since I'm going to get close to 3, so I'm going to say 3, something close to 3 would be like 2.9, 2.99. I want to see as I sneak up on 3 what happens. So I'm going to change the independent variable here to, what I'm going to do, I'm going to change it to ask. I want the calculator to ask me what independent variable I want, what x value do I want. So then if I go to the table, so I hit the second table, notice there's nothing in here, but I can put it in. Okay, so what happens as I get close to 3? Well, let's look at 2.9. That's 4.9. Let's get a little closer. 2.99. 4.99. And you could say, yeah, if I go to 2.999, I'm getting closer and closer to what appears, if I were to round this y value, the output value, looks like it's getting close to 5. Now, in this case, I could actually plug in 3, and I do get 5, but again, that's not why it's the limit. It's because I'm from the left-hand side, I'm sneaking up on, I'm getting close to 5. Now, let's sneak up to it from the other side. So we'll say 3.1. That's 5.1. Well, let's get a little closer. How about 3.01? Well, that's even closer to 5. How about 3.001? Okay, from the left-hand side, no, that's the right-hand side. Get our connections. So what we see happening here is that as we're getting x, we're looking at x going towards 3. So let's come here. As we come from this direction, and that we would write the limit as x goes to 3 from the left. We put this little negative sort of coming from the negative direction, but notice they're not all negative. It's really just from the left. That what's happening is our value is getting very close, our y value is getting very close to 5. Okay. When we come from the right-hand side, so we're letting 3 get closer and closer to 3 from the right-hand side, and we would list that as the limit as x gets close to 3. We put this plus, and that means from the right-hand side. It's also getting very, very close, but it's coming from this direction. So notice from the left, it gets closer from the bottom, and so we're circling on this territory of 5. And so we would say, numerically, we can see that this limit should be 5. Okay, so it's a technicality that we're not talking about the function value at this point. If we did, we could say that the function, say f of x at 3, it does equal 5. Okay, so that's a true statement. However, the limit's equal to 5 because coming from the left and coming from the right, the y value gets very close to 5. Okay, so we'll look at some examples where this function value doesn't exist, and some graphical examples as well. Okay, so how about this one? Notice as x goes to 2, if we plug in 2 minus 2, we get a division by 0. So we would be right in assuming that actually x equal to 2 is not in the domain. So how do we evaluate this one? Same tools we have when we go numerically. We're going to clear this out. We're going to put this function in. I'm going to go with the parentheses x cubed, and I have to arrow out of that, subtract 8, close off the parentheses, divided by parentheses x minus 2. And what I'm going to do is, I've already got it set up, but just to show you again, I'm going to look at the table of values. So I'm going to go to my table set. Notice it's still on ask. If it's not, I would arrow down and get it to ask, hit enter. And then I come second table to look at the table of values. Now, we don't want it to get close to 3. We want it to get close to 2. So you can't really clear these out. Actually, you can. I'm going to show you a tricky way. Let's come back down here. We'll change this to auto. We'll go to the table. And you see that 2 gives us an error. And you can do this with an automatic. So the way I'm showing you is not the only way, but it's kind of the way they support. And then we'll come back and we'll change this to ask now. And we'll go back to our table. Notice our table's been cleared out, so there's no junk in here. So what's close to 2 from the left-hand side? So again, I want to look at I want to look at what's happening here on a graph as I get close to 2 from the left. And what I'll do, so what are numbers close to 2 from the left? Well, let's just go with 1.9 and let's see what we get. 11.4. Let's get a little bit closer. How about 1.99? 11.94. We're getting, looks like maybe 12 might be it. Let's see. How about 11.999? No, 1.999. Where did I was? You see how I kind of jumped there. 1.999. A lot of nines. Yeah, 11.9. It looks like it's getting close to 12. But when I plug in 2 itself, I get an error because it doesn't exist. So so what I'm seeing is that as I get close to 2 from the left, so the limit as x goes to 2 from the left, I'm getting close to 12. Okay, and I'm coming there from sort of below, right? The values are sneaking up that way. When I go from the right, so what are numbers just a little bit bigger than 2? Well, let's go with 2.1. I got 12.61. Let's go with 2.01. Again, we're getting a little bit closer to 2. 12.06. How about 2.0001? Even closer to 2. There's our 12.01. So I'm getting close to 12 also when I take the limit from the right-hand side. And again, I write that as a limit as x goes to 2 from the right-hand side. I'm getting close to 12. So I will just say that this limit is 12. Now notice the function value does not exist at x equals 2. We see that right here numerically on the table. 2 gives us an error. It's out of domain. So the function value does not exist, but the limit does exist. And so very important for us, especially as in our calculus, this understanding of limit. So the limit can exist when a function value itself doesn't exist. A limit can exist when there is a function value, and we'll see there's actually a couple other options as well. So let's see. Let's now start looking graphically what's going to happen. So we want the limit as x goes to 6. Okay, we're going to check it from the left. So this is the value, the x value we want to sneak up on, and we want to record the limit will be what y value we're getting close towards. So as we come from the left, so that would be limit as x goes to 6 from the left, we follow the curve in this direction until we get very close as we want to x equals 6, and we're looking like y is going to -4. So I would say this limit, the left limit, is equal to -4. We also need to check the right-hand limit, so we check the limit as x goes to 6 from the right. And again, I should have my function in here. I'm just being a little bit crude in here, but just this concept, limit as x goes to 6 of the function. Okay, I'll go ahead and put it in there. Again, I'm coming from, what did I say? Is it 6 from the right-hand side? So I'm coming from the right, going towards the left. Okay, I'm also, the y value is getting as close to -4 as I want it to be, so I can say this limit is also -4. So since the left limit and the right limit are the same, we can say the limit does exist and is equal to -4. Now, the function value itself also exists, and it is also -4. So f of 6 actually does equal, so notice there's no limit on here, it's actually equal to -4. And that's one of the things we could say, well, when that happens, we have continuity, which is another important issue we get in calculus. But for now, we're just saying, hey, the limit's -4. Okay, so that's an example. Let's look at a few more graphical examples, and then we'll look at an affinity, and then you're going to try the homework on your own. Okay, so here's another limit. I created this graph, j of x, with decimals. And again, what we want to look at is what happens from the left and the right. So coming from the left, we trace along the function, and it looks like we're getting close to -2. Now notice there's an open circle here. There's garbage inside there too, but I couldn't get it out. So just there's an open circle. The function value is actually at 2 is +1. So we can see f of 2 actually equals 1, but the limit as x goes to 2, at least from the left, it's going towards that limit we would call -2. Okay. The limit from the right, which we write as the limit as x goes to 2 plus the limit from the right, again, we follow along the graph itself. And I'm just kind of going next to it. We're actually coming along. And what number, what y value are we getting close to? Well, we're also getting close to -2. So since the right and the left functions, say the right and the left limits are equal to -2, we can say that the limit is actually -2. Even though, in this case, we saw the function value is at y equals 1. The limit is at -2. So this is a case where it's discontinuous. The function value and the limit is not the same. Okay. It's one of the definitions we can use there. Okay, let's take a look at this one. Okay, again, we'll not necessarily write it all, but just kind of go along. So graphically, we need to see what happens from the left and the right to be able to talk about the limit. So here, this the left-hand limit as we get close to 2. Again, that's what we're focusing on here. X is equal to 2. X is equal to 2. We come along the graph, and this one, again, it doesn't matter that it's an open circle, but it's pointing towards -2. So we would say this limit would be -2. Coming from the right, again, we follow along the graph. We get a closed circle, but it doesn't really matter. We're looking, what are we getting close to? The y value that we're getting close to from the right is actually 0. So we get a right limit of 0, a left limit of -2. They're not the same. These limits are not the same. And so what do we say about the limit as a whole? It does not exist. There is no limit. Okay. Even though there is a function value, now if you ask me what's the function value of g of 2, right, we can say that that is actually, oh no, it's actually equal to 0, sorry, it's equal to 0 because of this point here, but there is no limit. There is a right-hand limit and a left-hand limit. It's what we're getting close to, but the combined limit, since they don't match, the limit itself does not exist. So be cognizant and watch for this. If if you see something like this and you get when you get to the limit as x goes to 2 and you've got this minus, it's only asking for the limit of one side. So and generally you'll get something it's getting close to. I guess there's always examples where it wouldn't. And then this is x getting close to 2 from the right. This actually does exist. This is actually going to be 0. This one's actually -2. It's comparing these two that we see that the limit itself does not exist. Okay, let's one more example. Here's, as you can see, and this one we'll do real quick, open circle, open circle. So this is one where the left-hand limit is -2. The right-hand limit coming along here, we're getting, the y value is getting very close to 0. So the limit itself does not exist. And when I actually try to find the function value at 2, it also does not exist. So it's like one of those where at 2, nothing exists. Okay. Very good. We're almost there for at least this first unit. So we're going to take a look at this last one and see what happens at infinity. So we'll take a look first at the first function, n of x, and yes, you can see we're going to do a fraction, so n of x does stand for numerator. So we can take a look at this numerically. If I can find my calculator here. So the way we can do this numerically is similar. We kind of sneak up on infinity, which is kind of hard to do. It's tedious, but we can get there. Okay, so we're going to put in this first function, 3x raised to the 4th minus 2x squared minus 4. What we're going to do is we're going to go to the table. I'm going to do this thing I want to clear out. I want to have a clear one. So I'm going to go back to auto. I'm going to go back to the table and let it go ahead and give me some values. I'm then going to come back to table set and change it back to ask. Just do this multiple times, partly because I want you to get the process down and to remember it. Okay. So now that we're on ask, I go second table, and it's going to ask me for values. Well, let's see what happens at 10. Oh, it's getting big. How about 100? Oh, 3e to the 8th. What is that? Well, that's a fancy way of writing 3 times 10 to the 8th power. So it's 3 with, what, 8 zeros behind it, something like that, 7 or 8. I forget which one it goes. But it's a very large number. And we go, let's go to 1,000. So as x is getting bigger, y is getting bigger. It's now to the 12th power, so 12 zeros. So the more zeros we put on the x, the more zeros we're getting on the y. It's getting very big. And just as we would expect, it's from algebra, we looked at in behavior. This does go off to positive infinity. We could look at the graph. It's a parabola, sort of a parabola, 4th power parabola. And so as x gets big, it gets big. So as x goes to infinity, we would say that this diverges. And so since it diverges, there is no limit, does not exist. Another word we use is diverges, which means it goes to infinity as well. So as x goes to infinity, y is going to go to infinity. But let's look at this interesting one here, or not that the other one wasn't, but not as interesting. What happens if we do it as a ratio? Okay, so we can do the same thing. We come back to our numerical. I'm going to show you a little trick. We're going to go second. Let me look a little over here. There's an insert, INS. Here it is. It's above the delete key. And that will allow me to insert a parentheses. I'm going to arrow over, put in another parenthesis. So there's my numerator divided by parentheses. And now I can put in this d of x. There's also some funky ways I can put in these in different ones. And I'll show you different techniques with the calculator to save you some time, but hopefully also help you remember these various calculator. I call them tricks. Some people don't like to use that word, but that's what it seems to be to me. So we've got this correctly. Okay, so we've got a polynomial divided by another polynomial. If you remember the section on, what do they call these? Rational functions. I'm going to discard everything. Let me get back into my slideshow. Here we are. So we kind of reviewed. Okay, so remember, this is really a DNE or diverges. It's depending upon how they ask it. Sometimes they want to know which way it diverges, so it diverges to positive infinity rather than negative infinity. Okay, so back here. If you remember from rational functions, all we really have to do is look at this first. These other terms become so small we can just ignore them. it's going to behave like 3 x to the fourth over x to the fourth, which if you were to do that separately, oops, x to the fourth cancels with x to the fourth. It gives us a 1. That's 3 over 1. That's going to be 3. Let's see if that carries through in the numerical analysis. Let's go to this table. And again, we got these weird, well, that's okay. This one, I'm glad I didn't reset it. I was almost going to, but at 10, it goes to 2.99. At 100, it goes to 2.9999. And then we see as x keeps getting bigger, we are getting closer to 3. We get so close to 3 that it just says it's 3. It gives up, right? Okay, so this little analysis here that we did back in algebra, it works. Let's keep them. So trick in algebra, it works, you know, with this analysis. We didn't really look at the left side and the right side because you can't really do that with infinity. You're just kind of getting there from one side. But we would say this one definitely goes to 3. If x goes the other way, but sometimes they would might ask the question, the limit. So we might also look at the limit as x goes to negative infinity. And notice the negative's in front of the infinity. It's not on this back side here. We could still do that by putting in negative numbers. And so I'll just change this to negative 10. What's happening? Oh, it's going, still going to 3. Wow, that's interesting. Negative 100. Negative 1,000. You know, as you get it big, it's still going to 3. Okay, so sometimes they ask you to look in the negative direction rather than the positive. So you can analyze both of these. But in this case, this particular question, both of their limits go to 3. Okay, and as you could kind of see, that's our last slide for this section. Take a look at the homework in Webassign. There's about 4 questions. In fact, while I'm here, why don't I just go ahead and make sure that you're able to get started on it. We're going to discard them this time. I'm not going to save that. Still getting comfortable with all of this, or uncomfortable as it may seem. Where is my, okay, Webassign. Let's get into Webassign. Okay, so you should have registered for this course, for the Webassign, paid your fees, $100 or something, or at least that's what it was last. I've got access to I copied this from the master course, and so right now we've got 10.1. I know it's not due till 8:30, but don't go by that. The idea is that you kind of go by the syllabus, and that's what we're doing. Is we're not forcing you to keep on a certain pace. We're allowing you some flexibility. But I always encourage flexibility that gets things done sooner rather than later. And this is from personal experience. I do tend to procrastinate, so I will understand it, but I'll tell you, life is a lot nicer when you're not procrastinating. Okay, so you'll get some limits like this with the rational functions. You'll enter in the values again here. This one looks like it's going to diverge, right? Estimate the limit numerically. So you could put this in because you got an x squared over an x. Again, that's the idea is you put this in your calculator, you let x get really big. But I'll just show you could put, I think in this one, it says D and E, and I think that's going to be right. Now, I can't check them individually when you're doing yours because I'm just in the view mode, but we could check it. So, and we can go with each of these. Again, just graph this. And what you want to do is you want to look from the left and the right, what's happening as x gets close to 6. Okay, there's some graphs. These are similar to the ones we worked on. So you're just looking in this case, what happens as x gets close to 4. And again, what they do is these red numbers are what gets changed. Sometimes they'll change them. And notice this is x goes to -4. What are we getting close to? Again, your answer is the y value that it's getting close to. There's a couple of here with some discontinuous stuff going on. So, and they'll ask for left side, right side, and what's the limit total. They'll even ask what the function value is, and they'll look at what's happening at infinity. And for infinity, we just have to extrapolate off. Okay. They've got some word problems, but they give you a graph again, and so you're interpreting what's happening again. This would say from the left side of 14.75. So coming from the left, what's the value? Coming from the right, what's the value? And then does the limit exist? Does the function value exist? Very similar to what we did. Okay, and some ways to answer these questions. What I want you to do is focus also on the wording, because this is important in business, is that you want to be able to apply these concepts to actual problems in the world. And that's what these last ones do. Okay, and then here's another one, kind of maybe draw a little graph, read through the situation. And this one is similar to the last example we did. You've got one function, and then you've got a ratio of functions, what's happening as you get close to infinity. So take a look at those, answer it, and then see if you can answer the questions about what the results actually mean. Wonderful. So get that work done. Monday morning, we'll meet up for our class meeting, and I'll be ready to answer any questions that you might have about this, about the conceptions, about the problems, and we'll keep moving forward. And then I will have a video ready for you for 10.2 by Wednesday, but maybe even by the end of this weekend for those who maybe want to work ahead. So if I'm going to encourage you to work ahead, I got to work ahead too. So we're in this together. Let's keep doing it together. Let's keep pushing ourselves just a little bit, and but keep ourselves comfortable too. That's an important thing to do. Keep comfortable with it. Keep processing it a little bit every day. That's sort of what I've been doing, trying to lose some weight. Address it a little bit every day. Don't, that's the best way to work. Okay, so take care, be well, and I'll see you Monday.